Out there, in the absolute zero of the interstellar void, it tumbled through in darkness unimaginable to us. For eons, it was a solitary pilgrim on an endless journey, a frozen shard of a forgotten Genesis, utterly alone. It knew nothing of light, nothing of warmth, only the crushing, silent cold between the stars and the gentle pull of galactic tides. Its voyage spanned millions of years, a silent testament to the sheer unfathomable scale of cosmic distance. This celestial nomad drifted through the gravitational deserts, a realm where centuries pass like heartbeats. Then, after a pilgrimage of such profound duration, a new sensation began to stir its ancient slumber, a whisper of gravity infinitesimally faint yet persistent, and with it a glimmer of radiance, the first it had known since being violently cast away from its own stellar cradle. Our sun, a distant, insignificant point of light, was slowly growing in its perception. The star's warmth, still feeble across billions of kilometers, began to caress its frosted, primordial surface. A ghost adrift for an eternity was finally approaching a shore. It was entering our home. It was coming for a visit. On the volcanic slopes of Mauna Loa under skies, so clear they seem like polished obsidian, a silent vigil is kept. Here, a pair of robotic eyes scan the heavens night after night. This is Atlas, the asteroid terrestrial impact last alert system. Its purpose is starkly practical, even existential. It hunts for celestial objects on a collision course with Earth. Its software, a complex tapestry of algorithms, sifts through an immense river of data, searching for faint points of light that move against the steadfast backdrop of distant galaxies. Most are familiar neighbors, asteroids on well-trodden paths. But on one particular evening, the algorithm paused. It flagged a smudge, a whisper of a presence so faint it was barely distinguishable from digital noise. An automated alert, stripped of all emotion, was sent to a small team of astronomers scattered across the globe. Initially, it was just another designation, a string of characters, another potential near-Earth object to be catalogued and tracked. Follow-up observations were scheduled, telescopes were trained, and the celestial suspect was placed under surveillance. The first calculations of its trajectory were routine, but something was wrong. The numbers didn't fit. The object's path was not a gentle closed ellipse, the familiar repeating loop of a planet or local asteroid. Its trajectory was a hyperbola, an open-ended curve. This was the mathematical signature of a tourist, a day tripper. It was not bound by our sun's gravity. It was merely passing through a stone, skipping once across the surface of our solar system's pond before vanishing back into the incomprehensible depths. A ripple of excitement, then astonishment, spread through the team. They had captured a phantom, a visitor from another star system. It was given a new name, one that signified its profound importance: 3I, Atlas. The third confirmed interstellar object ever witnessed. To understand the magnitude of this moment, we must journey back not just years but millennia. For most of human history, comets were not objects of science but terrifying omens, celestial portents of doom. They were seen as divine warnings, flaming swords brandished by angry gods in the tapestry of the night. The ancient Babylonians meticulously recorded their appearances, linking them to floods, famines, and the fall of kings. To the Romans, a comet was a stella crinita, a hairy star, its tail a sign of weeping and lamentation. The magnificent Bayeux tapestry chronicling the Norman conquest of England features a terrified populace pointing towards Halley's comet, a celestial spectator to the death of a king in 1066. For centuries, these apparitions were believed to be atmospheric phenomena, strange clouds or exhalations from the Earth itself. It was a brilliant Danish astronomer, Tycho Brahe, who in 1577 shattered this terrestrial illusion. By meticulously observing a great comet from different locations, he used the principle of parallax to prove it was far more distant than the Moon, a true resident of the planetary heavens. The celestial sphere was not perfect and unchanging after all. It was a dynamic, evolving place. A century later, Isaac Newton's laws of universal gravitation provided the mathematical language to describe these orbits. His friend Edmund Halley applied these revolutionary new tools to the historical records of cometary sightings. He noticed a striking similarity in the paths of comets seen in 153-11607 and his own observation in 1682. Halley made a bold, unprecedented prediction. He declared they were all the same object, and it would return around the year 1758. It was a prophecy rooted not in mysticism but in mathematics. Halley did not live to see his prediction fulfilled, but on Christmas Day 1758 the comet reappeared right on schedule. It was a triumph for science, a moment when humanity demonstrated it could comprehend the clockwork of the cosmos. The hairy star of doom was tamed, transformed into a predictable, if still breathtaking, celestial wanderer. In the 20th century, our understanding deepened further. Fred Whipple proposed the now famous dirty snowball model, describing a comet's nucleus as a conglomerate of ice dust and frozen gases, a primordial relic from the birth of the solar system. We began to send emissaries of our own to meet these visitors. In 1986, the Giotto spacecraft flew daringly through the tail of Halley's comet, capturing the first ever close-up images of a cometary nucleus, a dark peanut-shaped body spewing brilliant jets of gas and dust into space. Decades later, NASA's Deep Impact mission fired a projectile into Comet Tempel 1, creating a crater to study its pristine interior. And most spectacularly, the Rosetta mission spent 2 years orbiting Comet 67P, Churyumov-Gerasimenko, even deploying a lander to its surface in a maneuver of breathtaking complexity. We learned that comets were not just simple snowballs. They were complex worlds rich in organic molecules, the very building blocks of life. They were time capsules from 6 billion years ago. But all of these encounters, as magnificent as they were with members of our own celestial family. They were born from the same protoplanetary disk as Earth. Then came Oumuamua in 2017, a bizarre cigar-shaped object that tumbled end over end, baffling scientists. 2 years after the amateur astronomer Gennady Borisov spotted 2I, Borisov, the first object that looked and behaved like a familiar comet yet was demonstrably from beyond. And now 3I, Atlas. Another piece of an alien solar system had arrived at our doorstep. The world's most powerful observatories, including the Hubble Space Telescope, turned their gaze towards this new ghost. What they sent back were not just pictures, they were revelations, portraits of an alien artifact, and they were absolutely jaw-dropping. The initial images revealed a creature of ethereal beauty. At its heart was the nucleus, a mountain of alien ice and rock still too small and dark to be seen directly. But the sun's gentle warmth had awakened it. The ancient ices on its surface were not melting but sublimating, turning directly from solid into gas, erupting into the vacuum of space. This process created a vast incandescent cloud around the nucleus, a temporary atmosphere called the coma. Hubble's portrait of 3I, Atlas, showed this coma was not a simple sphere. It was a dynamic, glowing maelstrom of green and blue, a phantasmal shroud stretching for 100,000 kilometers. The distinct greenish hue was the signature of diatomic carbon molecules forged in the heart of a long-dead star now fluorescing under the sun's ultraviolet radiation. From this glowing head, two distinct tails unfurled a dual banner streaming across the solar system. The first was the ion tail, straight as an arrow, pointing directly away from the Sun, regardless of the comet's direction of travel. It was composed of gases stripped of their electrons by solar radiation, pushed back by the relentless pressure of the solar wind. In the new photographs, this appendage glowed with an eerie blue light, a delicate, almost invisible streamer of ionized particles, a cosmic windsock showing the direction of the Sun's invisible breath. It was a structure of pure energy, a ghost's ghost. The second tail, however, was the true spectacle. This was the dust tail, and it was magnificent. Broad, curving, and brilliantly white, it reflected the pure, unfiltered light of our star. It was composed of larger particles, grains of dust, and tiny pebbles liberated from the nucleus alongside the sublimating gases. Because these particles were more massive, they were less affected by the solar wind and more by the comet's own orbital momentum. They traced the path the interstellar visitor had taken, leaving a glittering trail of cosmic breadcrumbs. The images showed this dust tail was not uniform. It was striated, filled with intricate ribbons and filaments, evidence of episodic bursts of activity from the nucleus. It was a visual record of the comet's awakening convulsions. But the detail that truly shocked the scientific community was visible deep within the coma, close to the hidden nucleus. The unprecedented resolution of the new captures revealed not one but multiple brilliant jets of material erupting from the surface. These were geysers of gas and dust blasting out from active regions, fissures in the crust, where the Sun's energy had penetrated to the more volatile ices buried deep inside. Each jet acted like a tiny rocket engine, subtly altering the comet's trajectory in ways that pure gravity could not explain. Observing these fountains in such crisp detail on an interstellar object was a monumental first. We were watching in real time the erosion and dissolution of a body that had formed light years away in a completely alien environment. Imagine a perfectly preserved artifact sealed in a vault of absolute zero for longer than humanity has existed. Now imagine that vault is slowly being opened, and as light and warmth touch the artifact, it begins to transform and disintegrate before your eyes. This is what we were witnessing. The images were more than just pretty pictures. They were a forensic analysis, and they hinted that something even more dramatic was unfolding. A series of photographs taken over several days showed a horrifying yet scientifically thrilling development. The central condensation of light, the very heart of the coma, was elongating. Then it split into two distinct points of light. Soon after there were four. Comet 3, I, Atlas, was dying. The thermal stresses, the rapid rotation, the violent outgassing, it was all too much for its fragile structure. The interstellar messenger was breaking apart. It was committing a spectacular form of celestial suicide, sacrificing itself, and in doing so offering us an unprecedented glimpse into its primordial alien heart. This fragmentation, while a tragedy for the comet's continued journey, was an extraordinary gift to science. The breakup exposed fresh surfaces, layers of ice and rock that had not seen the light of any star since their formation. This allowed for a far more potent form of investigation to begin, one that doesn't rely on pictures alone. We needed to read the comet's chemical soul. To do this, astronomers employ one of the most powerful tools in their arsenal, spectroscopy. Think of it as a cosmic barcode scanner. When light from the comet travels across the solar system and enters a telescope, it can be passed through a special instrument like a very sophisticated prism. This prism splits the single beam of light into its constituent colors, creating a rainbow or a spectrum. But this is not a perfect, unbroken rainbow. Imprinted upon it are dark, razor-thin vertical lines. These are absorption lines. Each element and molecule in the universe, from hydrogen to water to complex organics, absorbs light at very specific characteristic wavelengths. Each one has a unique chemical fingerprint. By analyzing which colors are missing from the comet's rainbow, we can determine with astonishing precision exactly what it is made of without ever leaving Earth. The initial spectroscopic readings of 3I Atlas were tantalizing. As expected, they showed the barcode for water, carbon dioxide, and other familiar cometary ingredients. But as the comet began to disintegrate, exposing its deeper layers, the spectrum began to reveal something truly profound. The instruments detected an unusually high ratio of heavy water, or deuterium, compared to normal hydrogen. This isotopic ratio was markedly different from that found in most comets from our own solar system. Isotopes are like different flavors of the same element, with slightly different weights due to extra neutrons in their atomic nucleus. The specific ratio of these isotopes in a celestial body is a direct consequence of the environment in which it was born. A different ratio means a different birthplace. This was the first piece of hard chemical evidence written in the language of atomic physics, that 3I, Atlas, was unequivocally alien. But then came the true shockwave. As the fresh material vented into space, new, more complex fingerprints appeared in the spectrum, faint but unmistakable lines corresponding to long-chain carbon molecules. Glycine, the simplest amino acid, was tentatively identified. Amino acids are the fundamental building blocks of proteins, the essential machinery of life as we know it. Finding them on our own comets was revolutionary enough. To find them on a relic from another star system was staggering. It suggested that the raw ingredients for life are not unique to our corner of the cosmos. The universe, it seems, is universally seeded with the stuff of biology. This interstellar wanderer was not just a dirty snowball. It was a potential delivery vehicle for the prerequisites of existence. To truly grasp the violent beauty of what the images were showing us, we can turn to a more terrestrial analogy. Imagine a deep-sea submersible built to withstand the colossal pressures at the bottom of the Marianas Trench. Down there in the crushing dark, it is stable. Its hull contains a comfortable room pressure atmosphere. Now imagine that submersible begins a rapid, uncontrolled ascent. As it rises, the external water pressure dramatically decreases. The pressure inside, however, remains the same. The internal air begins to push outwards with immense force. The windows would bulge, the seams would groan. Eventually, the pressure difference would become too great. A weak point in the hull would rupture, and the internal atmosphere would explode outwards in a violent, catastrophic jet. This is precisely what was happening to 3I Atlas. For millions of years, it existed in the high-pressure environment of interstellar space, not a physical pressure, but a thermal one, the pressure of absolute cold which kept its volatile ices locked in a solid state. As it approached our Sun, the external thermal pressure dropped. In other words, it heated up. The ices deep inside its nucleus began to sublimate, creating pockets of high-pressure gas trapped beneath a cold, brittle crust. Eventually, that pressure found a weak spot and burst forth, creating the spectacular geysers captured by Hubble. The comet was quite literally tearing itself apart from the inside out, a victim of its transition from the abyss to the surface. This visitor was not just a passive object to be observed, it was an active, violent, and self-destructing engine of discovery. So where did this extraordinary object come from? What kind of stellar neighborhood could have produced it? To speculate on its origins, we must first understand our own. Our solar system was born from a vast spinning cloud of gas and dust. At its center, density and pressure grew until nuclear fusion ignited, creating our Sunday. The leftover material flattened into a spinning disk, a protoplanetary disk. in the warmer inner regions, rocky planets like Earth and Mars formed. In the colder outer regions beyond the frost line, ices could condense, allowing gas giants to grow and giving birth to trillions of icy bodies, the comets. Most of these comets were then scattered by the gravity of the giant planets. Some were thrown into the sun, others ejected from the solar system entirely, and a vast number were cast into a gigantic spherical reservoir far beyond Pluto known as the Oort cloud. Let's use an analogy to put this into perspective. Imagine our solar system out to the orbit of Neptune is the tiny solid core of an apple. The Oort cloud would be the apple's skin, a vast diffuse sphere of icy bodies gravitationally bound to our sun, but incredibly distant. Virtually every comet we have ever seen has been a piece of this skin, nudged by a passing star or galactic tide, and sent on a long journey towards the core. They are all part of our apple. Now, 3I, Atlas, is something else entirely. It is like a single seed from a completely different apple from a tree in an unknown orchard on the other side of the world. This seed has traveled across continents and oceans and has by pure chance drifted into our small part of the orchard. It carries the genetic information, the chemical blueprint of its parent tree, and the soil in which it grew. By studying this single seed, we can learn about an entire ecosystem we have never seen. The chemical data from 3I, Atlas, suggests it may have formed in a system much richer in carbon than our own. Perhaps it was born around a carbon star, a rare type of red giant with an atmosphere containing more carbon than oxygen. Or maybe its parent star was much larger and more massive than our Sun, creating different chemical ratios in its formative disk. The violence of its ejection also tells a story. To achieve interstellar escape velocity requires a powerful gravitational kick. It was likely not a gentle nudge, but a chaotic event. Perhaps its home system contained a hot Jupiter, a massive gas giant orbiting perilously close to its star, flinging smaller bodies out into the void like a slingshot. Or maybe its sun was part of a binary star system whose complex gravitational dance created zones of instability. Whatever the cause, this celestial orphan carries the scar tissue of a violent and tumultuous youth. This single object fundamentally reframes our place in the universe. It is a tangible link, a physical handshake with another solar system. For so long we have studied the stars through the abstract medium of light. Now the stars are sending us samples. This has profound implications for one of the most tantalizing questions of all: are we alone? The theory of panspermia proposes that life itself, or at least its fundamental components, can be transported between star systems, hitching a ride on objects like comets and asteroids. For a long time it was considered fringe science, but the discovery of amino acids on 3I, Atlas, drags this idea firmly into the realm of testable, plausible science. The comet's icy nucleus provides perfect shielding from the harsh radiation of deep space. Its journey, while long, was in a deep freeze, preserving its chemical cargo in pristine condition. It demonstrates that the very building blocks of life are not confined to our planetary cradle. They are cosmic vagabonds. Life might not have had to start from scratch on every habitable planet. The galaxy could be a vast interconnected ecosystem, with the seeds of biology constantly being exchanged over cosmic timescales. The arrival of 3I, Atlas, has ignited a fervent new ambition among space agencies worldwide. The next time such a visitor is detected, can we do more than just watch? Could we send a probe to meet it? The challenge is immense, almost beyond our current capabilities. These objects are typically discovered only when they are already close, and they are moving at incredible speeds. An intercept mission would require a spacecraft capable of unprecedented acceleration, a fast response probe that could be launched at a moment's notice. Projects like the European Space Agency's proposed Comet interceptor are being designed for just this purpose. It would wait patiently in space for a suitable target, then fire its engines to embark on a high-speed chase. To physically touch a piece of another solar system to drill into its surface and analyze its composition in situ would be a scientific achievement on par with landing on the moon. It would be like an ancient Roman scholar being handed a perfectly preserved library book from the Maya civilization. The knowledge contained within would be revolutionary. As quickly as it arrived, 3I, Atlas, is now departing. Its brief, violent encounter with our Sun is over. The fragmented pieces of its nucleus will continue on their path, fading back into the obscurity from which they came. They will never return. Our solar system was but a momentary distraction on an eternal voyage. We were privileged to witness its spectacular, fleeting performance. It was a ghost ship that sailed out of the fog, showed us a glimpse of its exotic crew and cargo, and then vanished back into the mist, leaving us with more questions than answers. It leaves us to ponder the sheer number of such objects that must be adrift in the galactic currents. Statistically, an object like 3I, Atlas, must pass through our solar system every few years. Most are too small, too dark, too far away to be seen. We are only now developing the technology to spot them. We stand on the cusp of a new era of exploration, an era where we no longer have to go to the stars because the stars are in a very real sense coming to us. These interstellar comets are nature's own probe missions delivering priceless samples from across the galaxy free of charge. Each one is a message in a bottle, carrying a unique story of its origins of a different sun, a different chemistry, a different possibility for how a solar system can be. The portrait of 3I, Atlas, captured in its final glorious moments, is more than just a scientific dataset. It is a piece of cosmic art that forces a profound shift in perspective. It reminds us that our solar system is not an isolated island. It is a port of call on a vast interstellar ocean. We are not alone because we are constantly being visited by the shattered remains of our distant stellar neighbors. The night sky, once a symbol of serene permanence, is revealed to be a place of constant transit, a grand central station for celestial nomads on journeys we can barely comprehend. And we are here watching, waiting for the next ghost to arrive.